In this video, I want to walk through the proof of security for a key encapsulation mechanism, or KEM, that is based on RSA. This is encapsulation. So encapsulation takes in the public key, which of course is N and E. We first sample an R uniformly at random from Z star N. We then hash R, which in the random oracle model means we're treating this as a public random function that maps from Z star N, which is where these elements come from, to some set L, which is a set of keys that's appropriate for some underlying symmetric encryption scheme. But for now, it's just some arbitrary set L. So we hash R to create a key that comes out of this set L. And then we create this wrap by taking R and raising it to the E mod N. So here's where we're actually using RSA. And then we return the wrap and the key. To decapsulate, we of course use a secret key. So we take the wrap, which is R to the E, and we raise the wrap to the D, which is the same as taking R to the E to the D, and we know E and D cancel each other, so that gives us back R. And then we're free to hash R to get the key, and we can return now the key. Okay, that's the RSA-KEM in the ROM, as we would call it. To remind you, so what we want to do now is in fact argue that this scheme here is a secure KEM scheme, and we want to argue it based only on the one-way permutation assumption for RSA. And of course the fact that we're modeling the hash function as being a random oracle. So to remind you of the KEM experiment, I've written it over here. So this is the KEM experiment for some KEM scheme pi and a security parameter lambda. To remind, the experiment is you start by picking a bit. You run the KEM key generation algorithm using the security parameter that outputs a public key secret key pair. You run encapsulation with the public key and access, since we're doing it in the ROM, this is the random oracle. And I say here that this is, we're modeling this as a random oracle, but rather than writing oracle H and then writing down the description of it, typically one just leaves this thing implicit, and the actual description of the random oracle becomes clear when you try to apply this definition to a particular scheme. Because for example, the domain and range may change depending on what actual scheme you're instantiating. So this is encapsulation. You run it with the public key. It outputs the wrap of a key K1. And then we pick key K0 uniformly from the set of possible keys from which K1 was drawn. And then we give to A the public key, the wrap, and K sub B, which is either the actual key that W wraps, or it's a K0, which is a uniform random key independent of W. We also give A access to the random oracle, and A's job is to output a guess at the bit, determining whether or not it's been given the key that's wrapped by W or a key that's independent of W. And the advantage, because we're doing a bit guessing game, is just twice the probability of winning minus 1. So that's the definition of the KEM experiment, and we want to argue that this scheme meets this security notion if RSA is in fact a good one-way permutation. So the way that we're going to do this is by a game-playing argument, and we're going to start with a game that just let me pull up the layering here. So we're going to start with a game G0. Let me scroll down. That's going to just basically implement the KEM game, this thing here, but substituting for encapsulation what encapsulation actually does. So here is game G0. And we're going to argue that, in fact, the security of this KEM scheme we just described here, the probability that A wins that game, is the same as the probability of this game outputting 1. So let's look at the game to make sure we're doing it right. We pick a bit, which is exactly what we do in the KEM experiment. We run, in the KEM experiment, you run the key generation algorithm, but in this case, that's just running the RSA key generation algorithm for the security parameter lambda. So you output N and E as the public key and N and D as the secret key. And then where we would run encapsulation in the KEM experiment, we just expand that into what encapsulation is actually doing for this particular scheme, which is to pick an R from Z star N, hash it, and then raise R to the E mod N and send that as the wrap. The rest of the experiment is continuing the KEM game. We pick that K0 uniformly from the set of possible keys, and then we give A the public key, W, and K sub B, and it outputs a guess at the bit. So this is just writing down this KEM experiment, but now specifically for RSA-KEM that we just described. The oracle here now, we do actually lay out what it is. It's the usual sort of thing for lazily sampling a random oracle. whose range is this set L. We pick a value of Z from L uniformly, and then we check whether or not a table that's keeping track of the values that have been asked to H, if the table at value X is not undefined, meaning it's already been touched, then we have to, of course, return what we returned before. And then we just rewrite into the table either this random value or the value that we wrote there before, and we return that. So it's pretty obvious just by looking at it that indeed this claim is true, that G0 running A outputting 1 is the same as the chance that A wins the chem experiment. Okay, so what do we notice now? Let's bring up the next layer. Notice that this happens here, this happens if and only if, well, so we're assuming, of course, that the adversary doesn't repeat random oracle queries because we know those are wasted. But this happens if and only if the adversary calls this oracle on a particular value, and in particular, this value, because this is the only other place that H is ever called. So H is called on this R as part of encapsulation, and that's going to set a value, right? T of R is going to be set to something. Everywhere else, the table is undefined. So the only way that this statement happens is if during its execution, A manages to call this thing on the value of R. So we're going to keep that in mind. Okay, so we're going to keep that in mind, and we're going to move to the next game. So I'll just slide this over. So we've done game G0, and we observed this thing about it. Now we're going to create from that a new game G1, and then from that as well a game G2. So G1, what are we going to do? Well, so we have replaced this thing here by the observation, which was that this thing happens if and only if the query that's asked X is equal to R. Okay, so let's go back over here for a second. So we are, as before, picking the bit. We're creating the public and secret key. We're doing encapsulation, which is you pick R uniformly at random. And what would have been here, let me scroll back over a bit, compare the two. What would have happened here is we would have called the random oracle on R. But what happens when we do that? A uniform random value is picked, and the table gets that value. So at R, the table gets the value we just picked. Okay, and if later on this oracle is ever called on R, we return that value. But we could just as well have picked the value that we for K1 uniformly from L, and then just later on said, well, if this guy ever gets called on R, then we'll use the value that we picked as opposed to picking it here. Either way, the distribution of this value is uniform over the set L. So that's what we do in G2. We just pick K1 uniformly from L. And then later on, if the oracle's ever called on this value R, then, well, we would trip this thing because that's the only way that this statement ever gets executed. And when we do, we say, okay, something bad happened, and we'll see why we call that bad in a moment. And so what we need to return now for the value of Z is the K1 that we picked before. So this is the same exact simulation. It's just where you're picking this value of K1. Are you doing it here, or are you doing it outside? And because we're doing it before A ever runs, we can just do it outside and make sure that we're consistent when we actually simulate the oracle. So let's just continue down. So we picked R, that's as before. This is a new statement. This is just raising R to the E, which we did before, and now this is continuing to pick K0 uniformly. So the rest of this is all the same as it was before. And so my claim is that, what did I do? Oh yeah, right. So the claim here is that G0 outputting 1, so this came over here, that probability is the same as G1 outputting 1. And we can see that that's true. G1 contains all the statements, including the box statement. So let's go have a look at the box statement. If we compare the oracle between here and here, we see that you pick Z uniformly, we run the check, which we just said was equivalent to this check. If this happens, then we're going to set this flag bad to true, but then we're going to do what we're supposed to, which is to take the value that we had written for Z before, which in this case is the K1 that we sampled over here, and we return that as Z, like we're supposed to. That's G1. And so G1 is behaving exactly the same way as G0, which is why this statement is true. Now, I've created from G1 a second game. So G1 includes this box statement, and G2 does not. So this is not here in G2. And because G1 and G2 are identical until bad, we know that we can write the probability of G1 returning 1 is upper bounded by the probability of G2 returning 1 plus the probability that G2 happens to set bad. And again, this is because these two games are identical until bad, meaning that any execution of G1 for any particular random choices made within G1, they will set bad at exactly the same time as they would in G2 because these two games are the same until bad gets set. It's only once bad gets set that the executions diverge. So this statement follows from that fundamental lemma of game playing, which says if you have two games that are identical until bad is true, then this inequality holds. Okay, so why are we calling this statement here bad? Well, it isn't really bad, but you can sort of see what's happening. Remember, we're ultimately trying to get to a point where we can build an RSA inverting, a one-way permutation inverting algorithm B for an RSA instance. And we can almost see, like, what is that adversary B going to get? It's going to get some x to the e mod n for a randomly chosen x. Well, here's that sort of a thing sitting right here. So we can imagine that we're going to use our RSA instance in place of this. The rest of it, we can do. We get the public key if we're an RSA adversary. We get the public key. We flip the bit ourselves. This R, because it's raised to the e, this is the x that we're trying to find. K1 we can pick, K0 we can pick, so we can run A just fine. The only place you tell me we run into trouble is if we get, we're simulating these random oracle queries. We can pick these values uniformly, but then we need to check, like if x equals R, then we'd have to, do the right thing. But we can't actually check whether or not the query thing is equal to R because in our RSA experiment, R is the thing that we're trying to return. So we can't actually check this thing. But what do we notice? Well, x is equal to R if and only if you take x and raise it to the e mod n and you get w, right? So let me check that again. X being equal to R was the thing we were checking before. That was, we realized over here, the only way that this thing gets set. But x being equal to R means if you take x and raise it to the e mod n and you take R and raise it to the e mod n, well, R to the e mod n is w. So we actually can do this check by taking x, raising it to the e mod n, and comparing it to w. And this is important because now maybe we actually can do write down an RSA adversary that can simulate this game G2. The other thing we notice is that we don't actually need the table anymore, right? Because now we're not actually using the table anywhere. So we don't really need to write values back in because remember, this statement is not here in G2. So all G2 does when asking a random oracle query is it picks this uniform random value, it runs this check, which we just said is equivalent to this check, and then it sets bad to true, but it never does this. It just returns whatever the random value was it picked before. So we don't even need the table at all, so we can get rid of the table too. Okay, so let's now move to game G3, which is just going to clean up a bit of things. So here's what we're going to do. Notice that in this game, the behavior of this oracle doesn't change whether or not bad is true. We always return this uniform random value. So we could just check for bad at the end of execution. We could just keep track of the values that are being asked. And then at the very end of execution say, hey, if I take the values that were asked and I raise them all to the e mod n, do I ever see w? If I do, then I should set bad. So that's what we're going to do in G3. We're basically just copying everything here. Here, rather than sampling two separate statements, I'm sampling them both in the same line. But everything here is exactly the same as it was in G2. The oracle, remember the oracle is just returning random values, right? It checks this value of bad, but it doesn't do anything. It's just returning this random value. So what the oracle in game G3 is going to do is keep track of what was queried and then just sample the uniform random value and return it. Now for the purpose of setting bad, as we just said, we can run A, let it finish its execution. Maybe A guesses this bit or maybe it doesn't, but we still have to check whether or not bad happens because keep in mind down here, there's two things we care about. Whether or not A actually guesses the bit in G2 and whether or not A sets bad in G2. Well, we notice that everything is the same. Everything up to this line right here, all of this is exactly the same as all of this. So the probability, and also this oracle's behavior is simply to return a uniform random value, which is exactly what this oracle does. So from the point of view of whether or not G2 running A outputs 1, in other words, A guesses the bit, that's exactly the same as if G3 running with A says, yeah, you guessed the bit, because it's exactly the same. This is the same as this, and this oracle's behavior is exactly the same as this oracle's behavior from the adversary's perspective. The only difference in this oracle is whether or not you actually set bad. So this statement follows from that, what I just said. Moreover, because the behavior of bad doesn't change, the behavior of the oracle doesn't change depending on the value of bad, we can just check whether or not bad happened at the very end of the game, right? Because from the adversary's perspective, whether or not bad is true does not change the behavior of this oracle. So we just collect up all those queries, and then after A runs, we say, oh, I guess I'm missing the return statement here too. Let me just write that in quickly. We need to return whether or not B prime equals B. Good. So we'll check this thing. We're also going to check whether or not bad would have been set to true. So we just check in this set of queried things x. We just say, does there exist an x in here such that if we raise x to the e mod n we get w? Because that's exactly the check here that would have set true. That was set bad to true. So again, we can now claim that the probability that in G2 bad gets set is the same as the probability in G3 that bad gets set. But now we've actually gotten somewhere, because if we slide over a bit more, look what we can do. We have now the ability to make an RSA, a one-way permutation adversary. This adversary we're trying to build is given the public key for RSA, which is N and E, and a value Y, which was made by, in the RSA one-way permutation game, some value, I'm calling it R. In the actual experiment, I think we called it X, but R gets picked uniformly at random from Z star N, and it gets raised to the E mod N, and that gets handed to the adversary. And the adversary's job is to return R, right? But we can actually simulate this thing. Look, every statement in here. So our adversary B can pick this. The public key is coming from the experiment here, so we just use that as a public key. All of this, like R, this R is this R. W, R to the E mod N, is this value Y. We can sample these two keys, and then we can run A. We run A with the public key that we're given, and with Y in place of W, and whichever of the keys the bit we flipped ourselves told us to use, right? So we run A, and at the end we just ignore whether or not it guesses the bit. We don't actually care. What we really care about is we need to come up with this value R, right? That's what we need to come up with. So in doing so, what we do is simply simulate this oracle as part of G3. We can always return uniform random values. That's easy to do. And at the end, after A finishes, we just take the set of things that it asked, and we can raise each of those to the E mod N because that's the public key that we're given. So we just try all of the X in this scripty X set, and we return the first one of them such that E to the X mod N equals Y, right? Because in that case, that means X is in fact equal to R, which is exactly the thing we were checking for over here. So this game we actually can simulate with a one-way permutation adversary for RSA. And that tells us then that this statement is true. So we already justified this, and now we're saying that G3, this thing sets bad if and only if there is such an X in here. But that's exactly when we would return the value that we're supposed to return, right? The X here will be the R here because of the way that we're simulating G3 using RY for W, okay? So this statement follows from that, and this probability is just the advantage. There's no scaling in the one-way permutation experiment, so this is just the advantage. How about this line here? I'm claiming that, in fact, the probability that we've already argued this piece, and now we're arguing that this is, in fact, equal to a half. Well, how do we get that? Well, look at everything that's here. We flip this bit, and we're generating the public key, so that's correct. We pick an R uniformly. We pick these two keys uniformly, and we raise R to the E, right? But notice now, like, these keys are actually independent of everything that A gets. A gets the public key. A gets the wrap of R, but it's getting either this uniform random key or this uniform random key. So we could, in fact, just, move this, as we've done before, till after that, right? Because the distribution of these two keys is identical. So we could just, give it one of these keys, fix it, say we're giving it K0, and then flip after, and see. It doesn't matter. That's sort of the point, is that the distribution on these two things is exactly the same. So it's independent, in particular, of the bit. Whichever one we give it, it doesn't matter. So it's clear that there's no information here that's actually being given to the adversary about this bit at all. Thus, its chance of guessing the bit is a half. So that justifies this. So now we can put it all together. So here's the punchline of it all. If you put all those steps together, what do we have? We had this probability was equal to this probability, which is upper bounded by these two. And we just argued that this one is a half, so that's this, plus this one is upper bounded by the B's one-way permutation advantage. We multiply this by 2 and subtract 1 to get the chem advantage. Well, that multiplies this by 2, which gives us 1. We subtract 1, so that goes away. So we just have twice this thing. That's our theorem statement. The RSA-KEM does, in fact, meet the chem experiment. You cannot distinguish keys that are actually wrapped by the chem from uniform random keys with probability any better than twice the ability of some adversary to invert RSA. So it's a nice tight binding. One thing to notice here is that you remember we had this similar kind of style of proof before when we were trying to reduce the security, IND-CPA security of Elgamal to, hashed Elgamal to the computational Diffie-Hellman problem. But you remember there we had like IND-CPA was upper bounded by was Q times some advantage over here, the CDH advantage in particular. And the reason we had that factor of Q there was because we couldn't actually do this test, right? We couldn't test each element that was in the set of random oracle queries individually. We just had to guess which one was right. But because of the structure of RSA, we can in fact just test everything. So there's no factor of Q loss. We just take this thing. We have a bit of extra running time, right? Because we have to actually go through all the things in this set. So our running time goes up by a factor of Q, or an additive term of Q, I guess. But we can actually do this check, which means we don't lose a factor of Q in the security bound. There's no guessing of which of these ones it is. We just test them all until we find it. So it's a nice tight bound. And that's your proof in the random oracle model that the RSA-KEM is secure if RSA is a good one-way permutation. And you have something similar to this on the homework to do. So you might want to make sure you understand this proof and just sort of follow it as you're writing your own proof for the homework problem.